Hello everybody, and welcome to this session. I'm happy to be here for the first edition of Days Amsterdam, so thanks for joining me. We'll be speaking about Retrieval Augmented Generation. So who has heard about Retrieval Augmented Generation? Yeah, pretty much everybody, a good proportion of you. So Retrieval Augmented Generation, that's a way to help LLMs better understand and become able to answer questions about your own data, your own information. And it's actually not very complicated to create an implementation of Retrieval Augmented Generation. But as soon as you're going to start to use your implementation, maybe you're going to notice that it's not giving the right results, or like the answers are not relevant or could be better, etc. And when I started exploring the field of generative AI a couple of years ago, I started playing also with this RAG pattern. And I felt that the results I was getting weren't that good. So I was like, there are probably techniques that help me improve the outcome of my search results. And that's why I decided to do this talk to cover those things. My name is Guillaume Laforge. I'm a developer advocate. I work for Google Cloud. I'm based in Paris, so I may have a little French accent sometimes. And feel free to reach me on social networks. I'm G Laforge everywhere, basically. Three key parts in this presentation. So we'll first, of course, start with an introduction, how RAG works, pros and cons, etc. Then we'll look at two kinds of techniques, ingestion techniques and retrieval techniques, which happen at different stages in the RAG pipeline or implementation. In this presentation, I'll be using a framework called LangChain4j. So this is similar to the LangChain Python frameworks, but reinvented for Java developers. And I'm also a contributor and even a committer on the project. And since I work for Google, I decided to help with the modules around the Gemini model support. So if ever you use those models and modules, that's my stuff. And LangChain4j comes with various useful components. So it's although if you use a model like Gemini, you've got a Java SDK that you can use. But if you use a framework which is somewhat of a higher level abstraction like LangChain4j, you get access to a lot more interesting components, like special components to access vector databases or databases with vector support. You've got components to split documents into small chunks, and we'll see how it comes into play in the RAG pattern, and many other things. So I won't dive and explain all the components, etc., but I'll show you some implementation details, how you can implement the techniques that we're going to have a look at today. So let's start with RAG. So the limitations of large language models, first of all, they are limited in terms of their knowledge because of their cutoff date. It means that their training data has been prepared at some point, and also the training of the model itself has ended at a certain point in time, which means that, for example, if I ask most models nowadays who's the Prime Minister of France or Canada, etc., I won't necessarily get the correct answer because it's not part of the training data, and it's past the cutoff date, so you don't get the latest information. Well, if you use tools like ChatGPT, Gemini.google.com, etc., they have search plugged in, so they can find more up-to-date information beyond what was in their training data, of course. Second aspect, of course, LLMs don't have access to your data. They don't know anything about your data. I mean, that's on purpose. If you have private information for your users, for private documents for your company, etc. And I mean, that's on purpose. It's a privacy aspect. You don't want an LLM to have access to your data. But if you want to build an application using LLMs that actually has access to your data, you need you need somehow to give and grant that access to the LLM. So we're going to see how RAG helps feeding the right pieces of information to the LLM to be able to answer questions about your data. Third aspect, hallucinations. Of course, unfortunately, LLMs hallucinate, and they don't necessarily know that they hallucinate, so they try to answer anyway because they've been trained to answer questions. So they always try to fill in the gaps, even if they don't know the answer, and it often leads to hallucinations. Last thing is, although there are models like Gemini with 1 million tokens context windows, most LLMs are somewhat limited in terms of the context window, meaning that you can't not necessarily feed all the data, all your customer data, all your documents, databases, etc., in the context window. So you cannot just, give all the data and ask questions away and get responses. It probably won't fit there. So we'll see how RAG helps here. So RAG, Retrieval Augmented Generation, so it's a kind of pattern, architectural pattern, so that you can prompt an LLM with and about your data. So RAG, there's the retrieval phase. We're going to search in a database or some search engine, etc. It could be Elasticsearch. It doesn't have to be like a vector database. So there's the retrieval aspect where, given a user question, we're going to find relevant documents or tables, etc., that may contain the answer. Then there's the augmentation phase where we use a specific prompt for the LLM, saying, okay, I have this little prompt here. That's an example prompt, but it's quite typical. So the prompt usually is, hey, you must answer the following question from the user, but here are extracts of the documentation that may help you find the, given that information, you should be able to answer that question. So that's the augmentation part. And then the generation, it's just the LLM's job to, generate responses. So that's where it's going to, frame and write the actual sentence. So some benefits, there's improved accuracy in the sense that the responses are grounded into the information you gave in the prompt, in the augmented prompt. There's less hallucinations happening because of that grounding, because it has to somehow answer with the information you're giving it. And of course, the data is as up-to-date as the data you give the LLM, right? So if the data you have in your databases, in your documents, is up-to-date, you're also going to get up-to-date answers. So you don't have the problem of the cutoff date, the training set last data information. And the other, maybe it's something that we don't mention enough when we speak about RAG, but for me that's the explainability aspect, in the sense that since we retrieved relevant extracts of documents, of data, etc., we can also show in the UI even that, hey, we found the information in this document and this document and this document. So if a user, it's a question of trust, a user asking questions can then have a look at the sources and say, oh yeah, that came from that document. Now I understand why the chatbot, the LLM, etc., answered that way. So it's a nice way to have more explainability and remove some of the mysterious aspects of how LLM works. Now let's have a closer look at the some kind of architectural diagram or sequence diagram in a way. So there are really two phases. There's the ingestion phase, and then there's the retrieval phase. So the ingestion phase is going to happen, at some point in another process, and then the retrieval is when the user will come and ask questions. So first step, ingestion. We're going to take all the documents, databases, text files, PDFs, whatever. We're going to split that into small chunks because we just want to look at extracts. We don't want to give the LLM full documents, just extracts with relevant information. We're going to calculate vector embeddings for each of these chunks. A vector embedding is like a big array of floating point numbers, and it's the internal representation that LLMs use to understand what a particular piece of text is about. So it encodes somehow the semantic meaning of the text. So for each pieces of text, you're going to have a big vector embedding. And we're going to store those vector embeddings in a vector database. And what's interesting with those vector embeddings is that vectors that are semantically linked or related or which mean more or less the same thing, the vectors will point in the same direction. So the distance or the similarity, the meaning that the vectors will be very similar. So you can use similarity or distance. The smallest distance you get, meaning that the vectors and thus the initial text chunks are similar or maybe mean the same thing. And what we found out was that a question vector embedding is close to a piece of text that contains the answer to that question. So that's why we're able to do vector searches and similarity searches. So once you've got all the data in the vector database, we're going to be able to do the retrieval phase when the user comes to your application and asks questions. So the user is here, the user is going to ask a question, it's going to go through your application, we're going to pass the prompt, and we're going to calculate the vector embedding for that query, for that question, and we're going to compare that vector with all the other vectors stored in the database. And as I said, a question vector and its vector embedding is usually close or in the same direction as a snippet of text that answers that question. We're going to create the prompt, the augmented prompt. Here's the question. Here are the extracts of the documents that can help you answer the question. And then it goes back through your application and you can show the answer to the user. But if you look at this diagram, there are lots of arrows. So there are potentially lots of places where things can go wrong or be inaccurate or potentially can be improved. So for example, did you manage to load and parse the documents correctly? For example, let's say in PDF, maybe you're only extracting the text, but what about the images? Or maybe, the document is not in the right format or something. So it's important to properly load and parse the documents. I said that we're calculating vector embeddings for chunks of text, but a chunk, should it be small, like a few characters or words, or should it be like full paragraphs, or what's the correct size for a chunk, if there is one? Is the chunk context relevant? So is it relevant to the actual question? So it's important because maybe we're going to fetch chunks that are unrelated to the actual question. I said that vectors of questions and answers or text containing answers are close to each other, but is it really always the case or not? Not necessarily, we'll see that. Also, did the LLM really include the answer? So although the augmented prompt contains everything, maybe the LLM didn't decide to answer according to that information. So maybe you could also improve the prompt potentially. So first, we're focusing on ingestion techniques, and then we're going to look at retrieval techniques afterwards. So the ingestion phase, so that's the top of my diagram. So we'll look at this part first, the chunking aspect. How does chunking work, and what can you do, what kind of techniques you can employ here. We'll explore the basic technique of splitting with a constant number of characters or tokens, but then we'll explore 3 more techniques like context expansion, hypothetical questions, which I like particularly, contextual retrieval. And there are many other techniques that exist. So as an example, I'll take a page from Wikipedia on Berlin. I could have taken Amsterdam or something else, but you'll see that it's interesting when we start splitting that document. So I've got an HTML page, but I'm interested in the raw text, not necessarily all the the Chrome around the page. So I'm going to extract the raw text of this page. So Berlin is the capital and largest city of Germany, etc. Let's say I'm using the naive chunking, and I want to chunk in chunks of 100 characters. So let's split that into 100 characters. Okay, why not? Is it too small? Is it big enough, etc.? We'll see. But there's something interesting here. So let's say I want to ask what's the population of Berlin. If you look at those 2 points, actually, even the bigger, I think that's the population for the whole region. What's interesting here is that the numbers are actually split over 2 chunks. So no chunks contain the information about the number of inhabitants. Okay, so it's problematic because if I ask the question, what's the population, it's not going to be able to answer the question correctly because none of those chunks contain the answer because of the way it's split. So one way to avoid that, and usually that's when you do like constant number of characters chunking, usually you do an overlap, which means that the first chunk is going to go up to here, so the number is still split, but the next one, the orange-ish kind of chunk, instead of starting here, it's going to overlap the previous chunk. So the first one still doesn't contain the right number, but the next chunk will actually start a little bit earlier here and will contain the full number. So that avoids the problem of splitting information across two chunks. So it's actually quite good. Another approach, after all, human beings write sentences for a reason. It's because a sentence carry and has the semantic meaning that the human being intended in giving that sentence. So chunking by sentence can be a very valid way of chunking. And what's interesting here is that we, of course, don't split some information across different chunks. However, one little problem here, if we want to answer the question again, what's the population of Berlin? If you look at this sentence, which contains the answer, it doesn't mention Berlin at all. So it's more than 3.85 million inhabitants. It's a European city, okay, but you don't know that it's related to Berlin. So an approach I've explored is actually using like a parent or parent-child relationship. So for example, you can embed a sentence, but you carry around the surrounding sentences, the context. Or you can split recursively by semantically by, let's say, chapters, then paragraphs, then sentences. But you can store, if you embed the sentence, you can store the paragraph within which the sentence is stored. So this is what I'm doing here. Let's say I split recursively. So I'm going to embed and calculate the vector embedding for the darker green sentence. But I will return, when I do the prompt augmentation, I will return the surrounding context instead of just the sentence. So having small chunk is interesting for when you do the distance or the similarity calculation, because it's going to match very well with the question. It avoids diluting because the bigger the chunk is, the dilution of semantic meaning will be across many sentences that could potentially be slightly unrelated. So that's an approach here. And the other potential problem with that one is that let's say you take a big novel. Sometimes you may have paragraphs that span several pages, so maybe that's a bit too big for a surrounding context, and instead another approach could be to just do a sliding window around like the sentence. So you split by sentence, but in the surrounding context you're passing like, let's say, one sentence before, two sentences after. So maybe let me show you that here. So let's say I've got some code here. Is it big enough, even in the back of the room? Yeah, awesome. So here I'm using Launch-Info.j. I'm going to load some documents, and I'm going to do a sentence split. And if the sentence is too big, I'm going to split by characters with an overlap. but most sentences should be fine, but it's really for longer sentences that I'm still going to chunk with a certain limit. And then I split and I get text documents. So I won't show you everything here, but notice this little function that I added before creating the embedding, storing in memory, etc. I've got this sliding window function. So it's a little bit of Java Stream magic here. Well, magic, not very magic, but I'm creating the sliding window of sentences. So I look at a particular sentence, but then I'm also adding like the certain number of sentences before and certain number of sentences after. And I'm going to decorate the text segment here, which represents a chunk. It should have been named chunks, I guess. But I add some metadata so that in the metadata of the segment, I'm going to add the surrounding context. So all the sentences before the current sentence and the sentences after that sentence. And it gives good results. So when I augment the prompt here, I'm going to give in terms of when I replace the question and then the extracts, I'm going to replace the extracts with here the metadata and the surrounding context instead of the one sentence that matched well. And I have a little demo here. So I loaded a few capitals, including Berlin. And let's say I enable RAG, and I'm going to use this hierarchical kind of chunking. And I'm going to ask, what's the population of Berlin? Okay. And let's see, it's going to search my vector database, and it's going to give me some results. And you'll see I've got some, so hopefully, yeah, it works. So, okay, 3.66 million inhabitants, and you can show the sources. So if you look at this, it returned 5 results, and it gives different search results. So which one contains, and interestingly, it didn't give the first sentence where it was 3.85. Where is it? Because it gave another one like this one. That was the vector embedding that was calculated for this chunk, but that's the context, the surrounding context that contained the actual information that it gave in the answer. Okay. So that's one technique. I'd like to show you another one which I like very well. It's called hypothetical questions. And by the way, when I put some small links here and there in the slides, it's pointers to articles or research papers that dive deeper into the topic. So I mentioned that we can do some hierarchical kind of splitting by, let's say, chapters, sections, paragraphs, sentences, etc. And if you do this recursively, you could actually stop at, let's say, a paragraph, but use what we call hypothetical questions, which means that for a given paragraph, you're going to ask questions you're going to ask the LLM to calculate or to invent some questions that would be answered by this paragraph. So for this paragraph, for example, an LLM could say, yeah, this paragraph can answer the following question: what is the capital and largest city of Germany? What's the population of Germany, of Berlin, etc. So for a given paragraph, I get a list of questions that can be answered. And what's interesting here is that if we calculate vector embeddings for those generated questions, the vector embeddings of the user query, of the question from the user, will be compared to other potential questions. So in terms of distance, in terms of similarity, comparing questions and questions should be even better than comparing things we know are semantically linked, like chunks and questions. So this is a slightly different approach, but it works quite well. So just remember, like you saw those distances, and we'll see if with this approach we can get better results. So we had the smallest distance was 0.56, 5. So let's clean the slate. What's the population of Berlin? Again. And it's going to compare my question with the other questions that were generated by the LLM. So let's have a look at what it generates. I'm on a wired connection, but somehow it's not always... Oh, it's even more precise somehow. And I have, again, 5 search results, but it compared to my question, the user question, what's the population of Berlin, was compared to this generated, LLM-generated question. What was the population of Berlin according to the 2022 census? Or this one was the population of the urban area. And you see that the actual distance is smaller, which means that semantically, yeah, there's a question over there. Yeah, I can show it in code, of course. So the distance is smaller, meaning that it's likely to be a better fit. And I'm still returning the whole context because, of course, a question doesn't contain the answer. So instead, of course, I'm returning the whole paragraph. So let's have a look at the code. Hypothetical questions. Let's move. So I define my Gemini chat model. And here, so here I'm splitting by paragraphs. Okay. So 2,000 characters. In case the paragraph is too big, I'm going to split by characters. And this is the part that's interesting here. So for each of those big chunks of text, I'm going to ask an LLM. Here I'm using Gemini. Suggest 10 clear questions whose answer could be given by the user provided text. And also I added this extra sentence, don't use pronouns, be explicit about the subject and objects of the question, because we don't want to have generated questions that are like, hey, what's the population of this city? Instead, you really want to have, what's the population of Berlin, Germany? So it's important to resolve the references, like pronouns, etc., to properly, have all the information, all the context. And then the rest is, the same thing as before. I'm doing some searches. So here I'm not using the higher, we'll see an example with a higher level abstraction from Langchain4j, but here, just to show how it works under the hood, I'm showing how I'm doing the search manually here. I want to get a certain number of results, a certain score I'm interested in, etc. It answers your question about the code? Yeah, cool. So hypothetical question, in my experience, works quite well. I quite like it. A few months ago, another approach was coined by Anthropic, contextual retrieval. Maybe I should add here that one downside, I would say, of this approach is that for each paragraph, you have to do an LLM call. So if you, if you've got really tons and tons of documents, doing tons of LLM calls, that's potentially a bit costly. But this approach by Anthropic is also similar. It's going to use an LLM, but I think its drawback is that it's even worse in terms of consumed tokens. And because we pay by the token, although it gives good results as well, maybe it's not ideal. But yeah, let me explain what it's doing. So again, we do big chunks like paragraphs, and we're going to ask an LLM to situate a particular chunk in the context of the whole document. So for each chunk, we're going to ask, so here's the chunk we want to situate within the whole document, but in each LLM call, you're going to pass the whole document each time for each paragraph. So in terms of token consumption, it's even worse than the hypothetical questions. And then please give a short, succinct context to situate this chunk, etc. So when you do this, I'm going to show contextual retrieval here. Let's start anew. What's the population of Berlin? And you're going to see that it says something like, yeah, this paragraph or this sentence is about this. So let's see what it says. Okay. So the city of Berlin, blah, blah, blah. So it gives a very precise answer. And you're going to see, let's come back here. So for example, this paragraph, was so we did the prompt that we showed earlier. This actual paragraph is about the introduction to Berlin, the population, the geography, etc. So it matches quite well with the actual question, what's the population of Berlin? Because, I mean, it contains both Berlin and population. So it gives quite good small distances, okay? So again, the sole downside, I would say, is the fact that it consumes a lot of tokens, so it's a bit expensive. And to do it, I can show you, I must have it open somewhere. So that's the prompt I had in the slide, basically. So when I calculate the embedding, I'm passing, where is it? So my prompt is here. So I'm passing the chunks and the whole document each time to calculate. I'm actually transforming the text segment. So I don't just take the chunk, the original paragraph, but instead I'm transforming the chunk to get the answer from the LLM. So I'm calculating the vector embedding with the what was generated by the LLM. All right, contextual retrieval. So we looked at a few techniques for the ingestion side, and we'll look at the retrieval aspect in a couple of slides. But two more things I'd like to mention is I decided to go with a certain embedding model, but the choice of embedding model to calculate the vectors is actually important. So for example, if you have an embedding model that is trained mostly on English, if you ask the question in Dutch, in French, or another language than the language that was used in the documents, then the vectors will be quite different. So instead, if you have multilingual documents, you'd rather use an embedding model that knows different languages very well. Because let's say the same sentence in English and the same sentence in French, with a good multilingual embedding model, they should generate very similar vector embeddings. But if you don't have a good embedding model that's only good in English, well, it will give very different vectors if you write in a language and have the answer in another language. So this is important. And also, for example, the embedding model I'm using in this application, it's actually trained on different tasks. For example, for fact-checking, for Q&A, for document similarity, etc. There are models that are further trained for specific tasks. So be sure to check the documentation of the vector embedding to see if it's got something for your particular use case. Then the database may be important. It can provide different distance or similarity calculations and formulas, or you can also do some further filtering. So for example, in my app here, you can see that I can then filter on the list of capitals or maybe the list of continents, because if you have to search through millions and millions of chunks and vector embeddings, it's going to be faster if you've got a smaller subset, if you can, and you know that there's a subset you should look into. But it means that you'll get more relevant vectors as well, not fewer, but more relevant vectors returned. So it can be important to choose an appropriate vector database. Okay, so now let's look at retrieval techniques. So that was the bottom of my diagram, where the user asks questions. So one thing that is important here, query compression, when you, especially for chatbot kind of use cases. So I've got this document, but maybe the dialogue, the conversation in the chatbot will be something like, hey, what's the capital of Germany? Where is it situated? And you see it, we're starting to use pronouns. Or how many inhabitants live there, right? But if you try to compare that question with what's stored in our vector database, we are losing some information. We'd like to know where, in which place do we want to know the number of inhabitants. So that's where we can use what we call compressed query. So if I show you, I can use query compression. Let's say use this one. So I'm going to do what it said. So what's the capital of Germany? So it should say, okay, it's Berlin. And then I'm going to ask the question, what's, no, how many inhabitants live there? So I'm not mentioning Berlin, but you'll see that in the sources, I will expand the sources for this second answer. It will reformulate the initial question. It should be at the top here. So instead of searching for how many inhabitants live there, it transformed the question into what is the population of Berlin, the capital of Germany. And it will match much better with the information we have in the data. So that's query compression. And in terms of code, so in this one, I'm actually using the higher level abstractions from Longchain4j. Oops, I don't want to type any character, which is more concise, but I mean, when I want to show you the actual how things are implemented under the hood, sometimes I have to go slightly at a lower level. So I embedded my content, I have my chat model here, and here I have my content retriever to say, okay, I want to search into my vector database, but I add an extra step, which is here, the query transformer, which transforms the initial question and looks at the dialogue we had, the exchange we had with the chatbot, to reformulate the sentence according to the various questions that were asked before. And that gives good results and a more precise question to search for. So that's a kind of query transformation as well. And the other example of transformation I'd like to show you, so you remember the hypothetical question approach that was at the ingestion time, but here I'm going to tell you about hypothetical document embedding, which is looking, so it's at a different level. Here, instead of comparing a question to a question like earlier, we're going to compare an hypothetical answer to our documents. So maybe we're able to use a smaller model with a smaller knowledge or something. We're going to ask an LLM to generate an answer. Do you know what's the population of Berlin? So it will use its internal knowledge, and maybe it's going to say there are 3 million inhabitants. It doesn't know the exact number, but it gives the correct structure of answer, of text, that will likely be present in the sources, in the documents that we have embedded. So we're comparing, we're searching for this, and it will match better with a similar sentence in the output, in the original. So let's see, where is it? Hypothetical document embedding. And let's reload that. And again, what's the population of Berlin? I could use another one, I guess. And you'll see how it reformulated things. But the fact that I'm using a big LLM like Gemini knows the world knowledge pretty well. So let's see. So without using RAG, it would have answered something like the population is approximately 3.7 million people. But that's what we search for in our vector database. So you'll see different figures here. Yeah, which one contains the answer? So one, I guess it's one of the surrounding contexts that contain the answer. And the other thing, so I think it's one in. It's in one of my next slides, reranking. I'd just like to mention reranking because you can also use reranking to ask an LLM. So let's do this. What's the population of Berlin again? Reranking is another way to look at the search results from the vector database. But why it's not showing the chunks? But it filters what's returned by the vector database to only return the relevant vectors that really answer the question. So it compares the question and the potential document that contains the answer, and it says, yes, the answer is contained in that document. So that's a way to re-rank, reorder the chunks, because sometimes it's not necessarily like the smallest distance or higher similarity vector that contains the answer. Sometimes it's a vector further in the search results. So re-ranking help reshuffle the results, only selecting and finding the best ones. And for re-ranking, you can use a scoring model in Langchain4j. And when you do the search, you can add, where is it? The content, you have a content aggregator, which will be used here. You define the vector database where you want to search, but you say, I want to use a content aggregator to re-rank the results. And re-ranking is also useful when you have different databases and you want to merge the results into one set of search results. Okay, retrieval. The other thing is maybe you have several databases, or you want to also use web search, and it's fairly easy to do in Langchain4j as well. So if you wanted to do that, where is it? Ranking, contextual. I thought I had it open somewhere. Oh yeah, or this one, query routing. So you can add a query router saying, yeah, search in the vector database, but also search on the web. And it's just a couple of lines of code in Langchain4j to do that. Metadata filtering, that's what I said. When you know that a question, maybe it's only about European cities, maybe you're going to look at vectors only that relate to cities in Europe. So you can do extra, where clauses, basically, in a SQL database. Reranking, that's what I just explained. But I would like to finish with something. So the last year was very much about RAG. That was a big keyword, a big buzzword. But I guess in 2025, you're hearing a lot about AI agents, etc. And sometimes, you saw how we were doing the search. We were searching for one particular question, one particular aspect, but what happens if the user asks several things at the same time? Instead of asking one thing in one question, maybe the user is going to ask several things at the same time. So the idea here, maybe I'll show you. So let's do this, and I'll just do, hierarchical chunking. Let's say the user asks, tell me about the population, the historical origins or regions, and the geographical situation of Berlin. That's actually 3 questions in one, basically, right? So if you search that, it's the 3 questions are merged into one, and maybe it's not going to give very good results. So I didn't try it. Does it say? So it talks about the population. Yeah, it's not doing too bad. But for example, it doesn't really mention the historical origins. Not really, yeah. So we'll see how we can, and the resources, it shows a bit of everything, but mostly population and a bit of geography, it seems. So it's not ideal, and you're not going to find the right vectors in the database because the question is too much diluted in terms of semantics. So you'd have to do a search for each different topics. So that's what we're going to look at here. But when you create AI agents, there's a key aspect that is important in AI agent. That's function calling, or also called tool use sometimes. So it's a way to help an LLM get access to information or external services or APIs, etc., beyond its internal knowledge. Let's say I want to know the weather in Amsterdam. LLMs don't know about live weather information, obviously. So instead, you give access to the model to, well, of course, the question, but you also tell the model, well, in case there are questions about the weather, there's this function, getWeatherString, that exists, that can be called to answer the question. So at that point, the model will reply back, hey, could you call that function for me? Because that's not the model that makes the actual call. That's your app that's going to, or the framework you use, that's going to do the call to the external API or service. So the app is going to say, hey, get weather with the parameter Amsterdam. The weather forecast system will reply, hey, it's sunny. And your app is going to respond to the LLM with, yeah, here's the information you were looking for. I called the function for you. Here's the answer that I got. And then the LLM is able to answer, yeah, it's sunny in Amsterdam. And you can pass the information, the response back to the user. And all the gray arrows here in the middle are not visible, are not seen by the user. So the user just sees the initial question and the final answer. So that's a way to extend an LLM to have access to external information, live information, services, or you could also imagine functions that do actions like sending an email, creating a ticket in a bug tracker, or whatever. So it's not just about fetching information. And as I said, AI agents, they have different characteristics. So they are able to do function calling. They are able to plan, like what are the different actions that need to be taken to answer the user query. They can also do reflections, for example, how they can think about, hey, here's the answer I got. Is it a good answer? No, maybe I need to do some extra searches and extra thinking to be able to answer. And often AI agents work as a team, and they can call other agents. So you've got a focused agent doing one particular task and another agent doing another particular task, and they can work and collaborate together. So that's how I'm going to introduce my Agentic RAG to answer more diffuse or diverse kind of questions, including those ones with several questions in one. So for that question, what's the origin, population, geographic situation of Berlin? I'm going to call a first agent, whose goal is going to identify the different topics. There are 3 topics here. Create questions. I'm going to use hypothetical questions for my searches. Questions related to that topic. Then it's going to collect the answers from other agents and tools, and then give the final answer. But this agent, I give it access to a history geographic tool, and that's that tool that's going to do vector searches in the vector database. And this particular tool is using another agent, which is my topic agent. The topic agent will get the results from the vector database and will create a report for that particular topic. So a topic will be the origins, another topic will be the population, etc. And it's going each time we're going to call that tool, doing a search, we're going to return one report for each topic. And then this tool is going to collect all the topics together and formulate a final answer. So if I do this, so I'm going to use agent, hypothetical question, and so what's the origin, historical origin, geographical situation, and population of Berlin. And it's going to do the search for me. And while it's doing this, I'm going to show you the code Agentic RAG. So it's fairly easy to do. You just have to, when you create the AI service, so I've got this interface here that Longchain4j is going to implement for me. And I'm going to say, okay, I want to use Gemini. I want to use an extra tool. I've got this new instruction here. And the LM will have access to a tool. And if you look at here, that's the definition of my tool here. The tool is here. I'm annotating things so that, okay, here you can do, and it's funny because this tool calls another agent. So I have another AI service. This one is going to do the RAG research, and it's going to fetch the result, create the topic back, and then it's going to reply back to the main agent. So it's fairly declarative. And let's see, yeah, so I got a report, historical origin, geographical situation, and population. So it's able to answer complex questions. And I also had just showing this. So if I run this like on the command line, you're going to see different questions for the different topics. So I've got a few questions. It gives different results for each question. And here, for example, number of inhabitants, etc. All right, so that's Agentic RAG. So there are easy questions and there are harder questions, and typically those like multi-hop kind of questions are the biggest, most complicated questions. Sometimes you have to answer several questions in a row before being able to answer a big complicated question, and the naive RAG approach cannot help with that. So you have to find ways to work around this, and an agentic RAG approach is a way to do this. We've seen quite a few techniques, but I mean, you can try to combine those techniques together. We tried to combine a few of them already in the UI of the application, but one size does not fit all. And a key aspect, but that's worth an entire talk that I didn't mention and cover in this presentation, it's evaluation. It's super important to do evaluation. As soon as you try a new technique, be sure to check against some golden responses, etc., or other metrics that you answer better with that extra technique that you're integrating. So it's super important to do proper evaluation there. So thanks a lot for your attention. You'll find some of the bits of code that I showed here in that QR code. So I'm already at time, but maybe I can take a few questions, or otherwise you're going to ask me after the talk. So thank you. But if you have questions, feel free to ask them while the other speaker is not there. One in the back, yeah. Yeah. Yeah, so for example, the anthropic technique that passes the whole document every time for calculating the vector embedding, preparing a chunk that will embed. You can use caching for those models that support that. So Anthropic has got a caching, for example, feature. Gemini also has caching available, so it's possible to lower the cost, yes. But it's still going to be expensive if you've got lots of documents, but a bit less expensive that way. Any other question? No? I'll be also around. There's a Google Cloud booth, so don't hesitate, and I'll be here the rest of the day. Thank you again.